So we're going to look at the initial value theorem today. In zTransforms, this is one of the very effective theorems when you deal with continuous time or discrete time systems and also the Z world, right? You have to switch back and forth for various things. And certain time domain parameters, if you want to calculate those parameters, signal values, etc., typically what you do is you transform from Z to time, right? And then you figure out your time solution. And then if you want to find out the signal at a particular point, you can read that. But this value theorem lets you figure out the initial value of your signal, maybe input signal, maybe response or whatever, right? From your zTransform itself. So that's why it's so important. Right, so let me show you this one. You can see it over here. A zTransform, xz is equal to x0, x1 is set to the -1, x2 is set to the -2, and so on. Okay, so it's one-sided zTransform. And in the time domain, you can see at time 0, the first sample is x0, and the second sample is x1, and so on. All right. So it's very clear. Everybody understand this much. And this is a zTransform. It's not time domain, but you can see time samples are already embedded in the zTransform. So if you take the limit, okay, if you take the limit of the zTransform as z goes to infinity, z goes to infinity, okay, and all these z to the minus terms, they reach 0, leaving only x0, right, on the right hand side. Okay, so you take the limit of both sides, left and right. Left hand side is basically x of z transform, and the right hand side you have this polynomial of z to the minus powers, and you take the limit of z goes to infinity, right? We take it to infinity because we see all these powers are negative. And then right hand side, what you remain with is only x0, that is the initial value of the function. Okay, so without ever having to inversely transform from z to time, right, by the simple trick of taking limit of z goes to infinity, you can calculate the initial value x0. All right, any questions? Right. In fact, I should have written this the other way around, right? Limit z goes to infinity x z on the left hand side, and on the right hand side simply x0. I will do that adjustment and post it. Any questions about that initial value theorem? Let's do a little example. You can see it over here. Xn be a left-sided sequence, right? Now it is left-sided sequence, not right-sided. Right-sided means you start at 0 and you go to the right, positive time, right? And this is a left-sided sequence, so which means you start at 0 and you progress to the negative time. All right. So the signal is equal to 0 for n greater than 0. All right. And n means timestamp 1, 2, 3, and so on, right? And you are given the zTransform as here 3z minus 1 plus 2z minus 2 over 3 minus z to the minus 1 plus z to the minus 2. By now you know that this is a rational polynomial of z to the minus powers, right? This is actually coming from some system. Okay, this is the system description. You are supposed to find x0. What is the in the time sequence, right? The first sample. So you have the solution here. I just want to show it to you how you do that after the theory. So for a left-sided sequence, right, you write your Z transform like this. Okay. If you look very closely, you can see the first sample x0 is there, as it was the case in the right-handed sequence. But after that, you can see x to the -1 and z. So this is the second sample on the negative time, the first sample on the negative side of time, right? So therefore, it is actually given x of -1. You can see -1 here. That is the time index, -1. And here you can see -2, right, on the left-hand side. And also you can see z to the power here is not negative, it's positive. Z to the 1 over here and z to the 2 over here, which means exactly opposite of what you have already seen earlier, right? So I think it's very clear, you can understand. Earlier it was right-handed sequence, which means 0 and towards the positive time direction, and now it's from 0 to the negative time direction. Okay, so just that. And now if you look at the polynomial sequence, because it is z to the positive powers, and if you see the motivation earlier, right, in the initial value theorem, right, the strategy was to send all the samples, right, all the terms other than the first one over here to 0, right? And that is why we took z to the minus, z to infinity rather, right? Because it was negative powers of z. But now you have z positive powers, so therefore sending z to infinity is not going to help. So we change the course here, and we are sending z to the 0. All right. So when you do that, z to the 0, right, limit of z to the 0, all the terms except for the first one on the right-hand side goes to 0. Clear? Right. So that is the theory of the initial value theorem, how it changes depending on whether you're dealing with a left-sided sequence or right-sided sequence. Okay. Right. So the answer to the question is only this much, right? X0, right? The first sample of the sequence is the limit of x z as z goes to 0, right? All the terms except all the terms with z to the minus powers, right? So now you look at this one, right? You need to do a little modification here, right? Even though it is left-sided sequence, right? Left-sided sequence, and it appears like this in the theory, but in the example, you are given negative powers, right? Negative powers. So this is completely free to formulate examples using either positive powers or negative powers, right? And also, when you look at the initial value theorem, right, it has two different formats. If it is a positive sequence or negative sequence, right? In case of positive sequence, it goes to infinity, and if it is a negative sequence, it goes to 0. Okay, so now the problem here is that you want to send z to 0. However, the example has given the rational polynomial with z to the minus powers, right? So that is the problem. If you just use the example as it is, right, then you can't solve this, because when you send z to the 0, the negative powers, right? So it's not defined. So what you want to do is you have to multiply negative the numerator and denominator of the rational polynomial with z to the plus 2, so that you can change it to something like this, as you can see it over here, right? Now it is all positive powers, right? Then you can substitute z to 0 and get the answer 2. Okay. The first sample is 2 in this case. Any questions, please? Anybody having any questions, any comments? All right. Now, if you look at the technique and generalize it, you would understand that the same technique can be used with slight modifications, right? To find out not only the initial value, I mean the first sample, but second sample, third, and so on, right? Can extend the theory to find other samples also. So let's look at that, how we do that. So we call this generalization of the theorem, right? To find the values of a causal sequence xn at n equals 1, right? And find x1 when x is like this. So we'll work it out as an example here, so that you will not only understand the theorem, but also be able to understand how you use that theorem to solve a problem, right? Now, this is a causal sequence. What I mean by causal is that you have z to the -1 powers, right? -1 powers, always going from 0 to right-hand side, positive time. And now we have no problems with x0, because you can use the initial value theorem and calculate x0, right? So let's move on from that point. Now x0 is something we know, right? X0 is something we know. And we want to find out x1, right? X1, the next sample. So you can find out x1, right? If you can reformat the polynomial, right, into what you have dealt with earlier, which means you have a sample and z and the second sample with z to the -1, third sample z to the -2, and so on, right? So the sample without any z will remain, and you can calculate the value, right? So in power series, this is something which is readily possible, and you have done this, I'm sure, in many occasions earlier. So the technique is we'll take z to the 0 to the left-hand side, like this, right? Now on the right-hand side, you have x1, z to the -1, and so on, right? And then multiply both sides with z, both sides with z. Right? Then what happens is that this z to the -1 goes out, cancels, and the second term z to the -2 becomes z to the -1, right? What you see on the right-hand side is something you have seen earlier, right? Can you see that? There is a term which is x1 without any z term attached to it. So now if you can eliminate all the terms with z, right, you will isolate x1 and you can calculate the value of x1, right? All what you need to do is to take the limit of this one, this term, right, as z goes to infinity, 0, or in this case infinity. Okay. Now you can actually extend this further, right? Manually you don't do that. You can write a little code, right, in MATLAB, and run it in a loop so that you can calculate first x0, then x1, then x2, and so on, right? You can calculate all of these things once you have the polynomial. All right. So this is how MATLAB is actually calculate the samples from a given zTransform. Any questions, please? Right. So if you want to remember, the equation is just this, right? X1 is the limit as z goes to infinity, z times xz minus x0, right? And to work that out, you should have calculated x0 in a previous step. There's an example, this one. Why don't you take a little time and work it out? So I'm giving you this one, right? This example, right? Get a little bit of practice. Find me x0 and x1, right? I'm going to give you a few minutes for that. All right. So this is the answer. X0 is calculated by taking the limit of xz as z goes to infinity, right? Because these negative powers of z. And then this is 0, this is 0, this is 0, and it's 2/4 half. Okay, right. And then you use the second theorem. In fact, the extension of the initial value theorem to calculate the second sample by taking z to infinity of this one, xz minus half, the whole thing multiplied by z, right? You have to calculate that one. So first, you better calculate that expression, right? Xz minus half, this is x0, and you get this expression, right? And then in front of that, you need to have another z, okay? This one. So it's eventually will be like this. You can see 13/2 z minus 1 because it's divided by 2, I guess, right? Because this half. Okay, right. And then you take the limit of that one, this whole thing, this expression, as it goes to infinity. Right, then this one is 0, this one is 0, this one is 6/4, which is 3/2, 1.5, right? That is x1. Okay, so this is an iterative algorithm. You can easily code it if you want. And once you have given the length of the sequence, right, you can calculate each term in the sequence. Right. Now, this one-sided zTransform, right, is what is most frequently applicable, right? Whereas in theory, you have the double-sided sequence, which is from infinity negative to infinity positive, right? But for all engineering applications, right, it is from 0 to infinity is one-sided. Now, one of the problems you have to deal with one-sided zTransforms is that when you shift it, right, if you shift it to the left or to the right, around 0, right, there's something happening, right? If there's a 0 at the middle, right, times 0, there's a sample. But if you shift it to the right, right, you are creating a gap here, right? So you can't create a gap. You have to pad up this gap with some samples, right? If it is just one step shift, you need to put the initial value there, right? We call it initial conditions. You have heard that in many applications, initial conditions, right? Or boundary conditions. And if you shift by 2 steps or 3 steps, n number of steps, right? You are creating the space, that many spaces, right? and you have to introduce these samples, right, before you can actually have the transform, a complete transform of the sequence. So this is what we are going to look at next. The shift property, right? Um, Now here you can see, look at this expression here, x n minus k over here. This is a time sequence which is shifted by k steps to the right. Okay, so you can call it this as a delay. You delay the sequence by k steps. All right. So if you have the original zTransform, right, how you can calculate the zTransform of the shifted sequence, right? This is how you do that. Z to the minus k within bracket. X is it. You can forget about this one if you want, right? Just say x1 is it. Summation in 1 to k, and you have a k number of new terms coming up. Okay, these are the new terms which are going to fill the space that you are creating, right, from 0 to the first sample of the shifted sequence, right? Otherwise, it will be a blank, empty space at time 0. So you have k number of steps, x minus n is it to the minus, is it to the n, right? So these terms are x to x of minus n. Minus n, what is minus n? Because partial systems, n is positive, 0, 1, 2, and so on. So we represent these new terms that we are going to introduce within the empty space as minus time samples. We are coming from minus time. When you shift it to the positive side, right, assuming there are things in the negative time, they are also being taken into the positive side across 0. So this is what happens here. All right. So for the moment we think that there are samples, right across 0, right? We consider only the samples at 0 and positive. But when you shift it, all the terms on the negative side, those terms are actually coming onto the positive side. But we don't introduce these samples as the samples of the sequence. We call them initial conditions. Okay, right. So don't worry too much about these minus k here, plus n here, and so on. When you work out an example, it will come very, very clear, right? And always, z to the minus power is the time position, right? Position of the sample. Now, to help you understand this theorem, let's take one step shift. Okay, only one step shift, which is in that case k equals 1. So it is x n minus 1. So you have the sequence, time sequence, and shifted by one step. Okay. If you look at the theorem over here, k is 1. Okay, it will be z to the minus 1 x1 z plus x of minus 1, because k equals 1 actually. So the summation from n equals 1 to k means 1 to 1, right? Only one sample, and it is 1. When you put it over here, it will be minus 1, and z to the 1. Okay. So this z to the 1 over here, and if you look at this 1, k equals 1, right? Minus 1. This minus 1 and this plus 1 cancel out. Therefore, there's no z over here. It's just x minus 1. Whereas for the first one, this is the sequence, right? Without any shift. Original sequence, right? Without any shift. And you multiply that Z transform with Z to the minus K because of the shift. I think you remember the shift theorem. You get the sequence, and then in front of that, you introduce Z to the minus K, okay, depending on how many steps you shift. So the first term here remains unchanged from the double-sided sequence theorem, right? In that case, you can simply confine yourself to the first term here. If there is no time zero restriction, and if the entire sequence is from negative infinity to positive infinity, right? There's no boundary in the middle. The whole thing moves this way or that way, right? So in that case, it's only the first term over here. But now, because there's time zero in the middle, and you have only one side, when you shift it, you want to introduce these new samples, right? They're coming like that, x minus 1. So we assume there's a minus 1 time, and there's a sample at that time, and now it comes to the sequence, right? X minus 1. What about 2 steps? You are shifting the sequence by 2 steps. So the new sequence is x n minus 2. Again, if you use the equation, you will see z to the minus 2 here, right? And this one is x1 z unchanged, plus you have 2 terms over here, n equals 1 and n equals 2, right? Up to k is 2 here. So when n equals 1, this will be x minus 1, z1, right? And there's another term, which is x minus 2 z2. Okay, so this z2 and this z minus 2 cancel out, leaving nothing. So therefore x minus 2 will remain as it is, whereas the other term in the summation, which is n equals 1 term, right, it will create x minus 1 z1. This z to the z1 multiplied with z minus 2 here, leaving z minus 1. Okay, so that will remain here. Okay, so this is how you actually determine the Z transform of a shifted one-sided sequence. Okay, so the original shift property that we have learned in the theorem, it contains only this first term, because when you derive the equation, initially you assume double-sided sequence, right? Negative time to positive time. But whenever you have the boundary in the middle, time zero, this is how you handle the Z transform with a shift, time shift. Any questions, please? Now, you can remember this sequence very easily because what you want to do is, if you have n number of steps, you need n number of samples here, and they're coming like x minus 1, x minus 2, x minus 3, x minus 4, and so on. And then for each term, you put a z to the minus 1, and then 0, and so on, right? Because this exponent here is it to the power, right? So you have to start with a value, right, which is equal to the time shift, If you're talking about 5 steps, you start with z to the minus 5, and then z to the minus 4, then z to the minus 3, minus 2, minus 1, and no z last term. Okay, so it goes like that. So the shift theorem can be illustrated like this for you to understand what's happening here, right? Z n plus k, right? So this is a case where you are shifting the sequence to the left, to the negative time, right? Left shift. In that case, it is n plus k. Earlier, it was minus k, right? And if you follow the sequence, and it will look like this: z to the k this time, x of z minus n0 to nk minus 1. There's a slight adjustment because of the the time sequence, right? Xn is to the minus n. So the the equation is slightly different than what we have seen earlier, but it explains the same principle. When you're shifting this way, right, you are putting more samples here, and you are shifting that way. You don't have to put any more samples, but you have to take out some of the samples. Okay, you have to deduct some samples. That's what happened, right? Because earlier you created an empty space gap, which you fill with samples, right? That's why you had plus here. You are adding samples, but now you are moving that way, right? Across time 0. Some of the samples, like first samples, x0, x1, x2, like that, now you have to get rid of them because they are not in your time. It's negative time, and we don't consider negative time. So if it is one step, the first sample x0 goes out. If it is two steps, two samples go out, like that. Now let's talk about just one step shift, right? N plus 1. So then the equation would be z to the minus z to the 1, x is at minus summation n0 to k minus 1, which is also 0, right? 0 to 0. Then this is x n z to the minus n. It will be just one sample going out, which is x0, right? So this is it comes over here minus z x0, right? So if you look at the illustration down here, right, this is the unshifted sequence x0, x1, x2, x3, and so on, right? And then you're shifting it to the left by one step, right? And this sequence is at x0, this one minus x1, right? Get deducted with this one. So these two terms cancel out. Okay. The new sequence is actually starting with x1 here, x2, x3, and so on. All right. So these are little modifications to the shift theorem to accurately represent the remaining sequence after the shift, right, left or right. So what you need to understand is that if it is a right shift, you are introducing new samples in the empty space. And if it is a left shift, you have to take some samples out of the original sequence. Okay. And the two equations given will take care of that. Any questions, please? Is everything clear to everyone? Okay. So let's work out this example. Find the solution of the following linear constant coefficient difference equation. Right. So what is that? If you look at here, right, this is a difference equation. Yn is equal to 0.25 yn minus 2 plus xn. Right. There you can see the difference equation. Y is the response, basically. X is kind of sort of input, right, to the system. So both these two sequences are connected like that. A very simple difference equation. Now, how do you get this kind of difference equations, right? You can imagine a situation where there's a system and there is an input to the system and then a response out of the system, right? And in continuous time, you can actually model this using a transfer function, input, output, xn, yn, okay? And then when you discretize it, right, you bring the transfer function into a difference equation or ordinary differential equation into a difference equation, right? So that is this one. We will look at that in the next chapter, right? But for the moment, remember, this is what is called a difference equation, which is actually coming from a differential equation after linearization, okay, after the discretization part. And here you are given xn, the input to the plant, as delta n minus 1. Also, you are given y minus 1, y minus 2, both ones. And the moment you see these ones, right, y at time minus 1 and y at time minus 2, right, you can actually safely figure these samples into initial conditions, right? In the shift theorem, you have these samples, new samples coming from the negative time. So minus 1 time minus 2 time, the two samples, they're coming now into the equation because you're dealing with the shift here. Obviously, you can see y n minus 2, right? So why don't you give it a try? You have the difference equation and you have xn, right? And you are given the initial conditions, right? Y minus 1 and y minus 2, right? Take a little time, 2 minutes or 3 minutes, right? And find me the solution of the difference equation. That is, what is yn? So when I say yn, which is already given, but it's not the solution, right? It is how things are connected. It is the system model. What you are given here is the system model in discrete time. What I'm asking you to do is find me the solution of the system, which means what is yn as a function of n. Yn as a function of n. You can't have yn previous samples of y or xn in the solution. Okay, please understand the difference between this equation, what you see on screen, right, and the solution. You are asked to synthesize the solution, that is yn equals something as a function of n, only n. Okay, you can't have anything else. It should not be a iterative equation, right? Of course, if you look at this one, right, you know xn, you know y initial condition, you can substitute and calculate y1, y2, y3, y4 as an iterative loop in programming, right? This is what you do. That is not you are asked to do. You are asked to mathematically solve the problem and find out yn equals function of n, okay? So that you don't have to iteratively run this one, but straight away, if somebody asks what is the sample n equals 10, you have the equation, you substitute n equals 10, you get the answer, okay? So get me that kind of solution for this problem. So you get about 3 minutes from now. Okay. Has anybody done it? Anybody who has done it and got the answers, please let us know. All right, in that case, I'll show you the answer. So remember, you're getting these problems, right? All the time in the discrete time, digital controls, right, etc. Your plant and the input are all in discrete domain, right? So you need to remember this theorem, shift theorem, how you handle it in one-sided sequences, right? Okay. So the difference equation, which is given like this, 0.25 yn minus 2 plus xn, right? You have to transform this into Z domain, right? How do you do that? You will see this yn minus 2. This is the shift, okay? Shift to the right-hand side by 2 steps. So you have to bring in the Z transform when a sequence is shifted to the right by 2 steps, right? Which is given like this, okay? Coming from the theorem straight away. So on the right-hand side of this equation is the Z transform of the shifted sequence, which is this one, yn minus 2. When you transform this into Z domain, it will look like this. It will look like this. Not only the first term here, z to the minus 2, why is it? This is what you see in the table, because table has been created for double-sided. The whole sequence moves this way, that way, right? There's no gap or boundary in the middle. So when you shift the sequence, double-sided sequence, you are not creating a gap anywhere, right? The whole sequence moves, right? There is a gap at the end, but that is infinity. And so if there's a gap or not in infinity, we don't care, right? That is how the infinity is defined in the first place. Right. So let's look at this one. You have y minus 1, which is an unknown. Y minus 2, it's also an unknown. And to proceed with this example, you should be given these initial conditions. Of course, you are given, right? So you plug it in here, 0.25 times. In place of yn minus 2, you plug in this entire sequence here. Can you see that? This is the Z transform. And after that, you have xn, and the Z transform of xn is xz. Okay. So left-hand side is yn, then Z transform of yn is yz. Right. Now over here, you are in the Z domain. You have converted your difference equation into Z domain. This is what we do in solving difference equations, right? Very similar or analogous to you transforming differential equations, right, to Laplace domain. Here, what you do is you transform difference equations into Z domain. Okay, right. Now, on the right-hand side, you have xz. What is that? This is the Z transform of xn, and xn is actually delta n minus 1. So what is the Z transform of delta n minus 1? Of course, it is Z minus 1. Z transform of delta n unshifted sequence, and which is Z to the minus 1. Okay, all right. And if you look at this as another shifted sequence, well, you can do that exactly over here. And you are getting y minus 1, right, in the sequence. And the delta sequence, they're all zeros. So therefore, there's nothing other than Z to the minus 1 over here. Okay, right. So let's substitute Z to the minus 1 in place of xz here. Then you have a complete Z transformation. So the values given for y minus 1 and y minus 2, right, you can substitute over here. They're both 1, I think. What is the value for, yeah, they're both 1, right? So you substitute 1 and 1 over here, right? Over here, right? And Z to the minus 1 for the Z transform of xn. And after that is simple arithmetic, right? I don't want to go through each and every step. And finally, we get to yz as a rational polynomial, this one, right? Please try to understand the process, right? And make sure you are able to do this yourself, right? I'm not getting enough feedback to know whether you are following me or not, right? But this is not very difficult thing. This is something very simple in a way. So you are supposed to be able to handle this mathematics, okay? And in the paper also, there will be Z transform based questions related to control theory, right? Not basically mathematical proofs and all that. I'm not going to test you on that, but certainly you will be tested because these digital control systems, right? And this is very fundamental. All right. Now, it's entirely a mathematical strategy that you need here to solve this, right? Is rational polynomial of z to the minus powers. So let's break it down into first order terms, right? Partial fraction expansion. And you can see in the denominator is second order. You can break it into this one, this format, right? And get the two partial fractions like this. And then calculate A and B, you can use the cover-up method. I think we have discussed that earlier. Right, so this is how you calculate A. You get HZ, the entire expression on the right hand side, multiply with the denominator of the first partial fraction, and then get Z to the minus 1, 2, which is the first root of the expression. If you look at this one, is the first root and this is the second root. Okay, the first root and second root. You said this entire thing equals 0, right? And then calculate Z or Z minus 1, whatever it is. In this particular case, we always have Z minus 1. So therefore, I think it's okay if you calculate the value for Z minus 1, not for Z, okay? Because when you substitute, you are substituting for Z to the minus 1. So therefore, use this minus 1 together with Z as a 1 unit, okay? So if you write this entire thing equals 0, Z to the minus 1 is actually 2, right? Is 2. And here, if you said this entire thing equals 0, Z to the minus 1 is minus 2. So you substitute minus 2 when you calculate B, right, for Z. And then you substitute 2 for Z minus 1 when you calculate A using cover-up method. Right, so this is the cover-up method for A. You substitute Z minus 1 equals 2, and you bring it through. Eventually, A is 11 over 8. Okay, and if you do that for B, right, you substitute for Z minus 1 minus 2, right? And the answer is minus 9 over 8. And then you substitute for A and B, 11 over 8 and 9 over 8 minus, and you have this nice first order two partial fractions, right? And beauty is that you have seen these formats, right? This one and this one, same format in the Z table, right? So when you see something like this 1 over, forget about 11 over 8, 9 over 8, they are just coefficients, right? But other than that, what you see here is that this is 1 over 1 minus something times Z to the minus 1, right? And here also it is 1 over 1 plus can be regarded as minus minus. So it is 1 over 1 minus alpha Z minus 1. So it's pretty clear that the inverse Z transform of this one is, right, this coefficient over here minus half to the n. If you check it with the table, you can see it. Here, the inverse Z transform is this number here, which is negative half to the power n. Okay, just that. And you have this 11 over 8 over here and 9 over 8 over here. And if you look at this one, this is yn. So when you solve yn into a form like that, which is a function of n, the only unknown on the right hand side over here is n. There's nothing else, right? There's no previous samples of yn or xn or anything. It's just a function of n. When you solve it to that format, we call it a solution, so that you don't have to program these, but you can substitute n equals 10, 20, 50, 30, whatever it is, you calculate your yn. Okay, so please take that down and calculate me the first 5 samples, right? First 5 samples, n equals 0, 1, 2, 3, 4. And if you want to calculate what is the 50th sample, n equals 50, put it there, right? And figure that out. Right. That is a sizable example. If you go through that example, right, you will understand the theory, you will consolidate your knowledge about the theory. Not only that, you are able to develop your skills of how to use that theory in solving practical problems like this. Okay, great. Any questions, please? Any questions? Shamira, is everything clear to you?
Yes, sir.
All right. What about the others? Chaturanga, is everything clear to you? Dayavansa, is everything clear to you?
Yes, sir, everything's clear to me.
Okay.
For the moment.
Right. Dylan Fernando.
Yes, sir, it's fine.
Fine. Tilanka.
Okay.
All right. Hevavasam. Is it clear
Yes,
to
sir,
you?
it's fine, sir.
Right.
Clear, sir.
All right. Ramesh.
So it's fine.
Sanjeev Kant.
It's clear, sir.
Clear. Right. Then Vihangi.
Yes, it's clear.
Okay. Vijay Tilaka.
Yes, sir, it's fine, sir.
Right. Jokshan. Jokshan AK. Is it clear to you?
Yes, sir. Yeah.
All right. Good.
Clear.
Good. So yeah, that's great. Right. Let's do a little homework here. So I really want you to use your develop your skills during the class rather than trying to spend a lot of time trying to catch up unknown things, right? I'm sure you don't want to spend more time than what is really required for anything. Okay. So if you can learn something within half an hour, why you should spend hours and hours, right, catching up? That's totally unnecessary. So this time is that time for you to catch up everything. So let's work it out. Let's take homework 1. We want to solve this problem. And also during the class, right, you better write down notes yourself, right? And write down the theories and all that, sketch it, right? Scribble it on your paper, right? Whenever I ask you to solve some problems, right? Sometimes you can't see all the slides, right? Remember before the last break, I pedaled back few slides to show you the shift theorem, right? Because I thought you might not have written it down. So important ones, you write it down. Do not just rely on the lecture notes, right? Because these notes will be provided to you anyway, but during your learning process, you must write yourself certain things, right? Okay, so this is one we need to work out. What is it? A discretized system is given by this difference equation. Again, then you have another difference equation. Remember this. Very similar to what you have received in the first semester, right, with regard to systems, right? That is transfer function. You keep getting transfer functions, right? It's very familiar to you. A system is described by the following transfer function, right? Now here, it is difference equation, right? So you get this difference equation, or transfer function is a domain, okay, either way. Now, if you look at this difference equation, you can see yk plus 2, 0.5 yk plus 1, 0.1 yk, which is equal to minus 0.3 times 0.5 k. Okay. So can you solve for yk? Yeah. The question asked is solve for yk. Now here, if you look at that one, samples of y are related together. So it's like a propagating wave, right? You have yk plus 1 and yk plus 2. The three samples, they are related to each other. So when one changes, it propagates to the other one, propagates to the other one, and it goes like a wave, right? It goes like a wave. So there's a pattern here. There's a pattern here. And also there's some sort of energy coming from external sources, like input. But in this particular case, it's already given numerically. It is 0.5 to the k. So that this is the energy pumping signal from outside. Okay. Now with that, are you able to calculate for yk in a future time? This is the generic format, k plus 1, k plus 2, right? Give it a try. So we'll take another 5 minutes for that. I have worked it out just the initial few steps, right? So that you can get some idea and then try to continue. Please do that. All right. Anybody has been able to work it out? Please raise your hands, those who have been able to solve the problem. No one? All right. So it's a bit tough, I know. So let me show it to you. Right. So this is the answer. So you have the discretized system given like this. And we want to transform this into Z domain and then solve the problem there and do the inverse transformation. Okay, right. So this one we transform to Z world like this. Okay, and there are no initial conditions given in the example, like what is y minus 1, what is y minus 2, and so on, not given. So therefore, you have to assume that this is a double-sided sequence. So there's no need to pad up or fill the gap at 0, right, by bringing in new samples. So it's kind of easy then, right? You can take the zTransform right from the table without any modification, right? So it will be Z2 YZ. Remember, this is k plus 2, okay? And then this is k plus 1, which means Z, Y, Z. And yk becomes YZ. And on the right-hand side, anything to the power k, right? The Z transform is Z over Z minus 0. Which is this value here, the constant, okay? That is the first step. And then you simplify and isolate YZ on the left-hand side and take create this polynomial of Z to the positive powers, Z square plus 0.5 Z, sorry, 0.4 Z plus 0.1, okay? And bring it to the right-hand side together with this one. And you create this rational polynomial of Z on the right-hand side. And if you look at the denominator, you already see one first-order term here. This is the quadratic expression. You can break it down into first order factors like this. Okay, this quadratic expression, it can be written like this, and it'll be a complex number, right, for the two factors here. And if you want to figure that out, the poles and so on, right, they are complex pair of conjugate poles, right, conjugate pair. Okay, right. You can hear me well, right? Somebody has written, you're not hearing sometime back, right? Okay. Now the thing is, how can you break this down into factors, right? So that you can inversely transform them into time domain. Maybe some of you have gone up to this point and stuck there. So this is how we do that. Same cover-up method, you can do it and get the three factors like this, right? Maybe you are a bit shy to make it a move, right, at that point. But if you proceeded, you would have gotten these expressions here. The second term, the third term, right? Then you can see this is 0.826 e to the minus e to the j 1.234, and same here 0.826 e to the minus j 1.234, right? So what's next? And the first term here, right, remains unchanged. Is it or is it minus 0.5, right? You just keep it, you bring it there. But if you want to do the inverse transformation, then it's simply 0.5 to the power k, right? K is the time index in this case, right? What about this one? This is again, you can inversely transform. If you look at the table, right? Z over Z plus something. So you get this something over here, right? Plus the constant and raise it to the power of k. This is exactly what is happening here. Minus 0.2 minus j 0.245. This whole term in negative, right? To the power k. In front of that, you need to have e to the j 1.234 anyway. And in front of that, you need to have 0.826. Here is the same story, right? You have this constant 0.826 e to the j this thing. And then after that, z over z plus this whole thing, right? You get this constant as negative 0.2 and then positive j 0.245 and raise it to the power of k. That is inverse Z transform. Okay. So then what do we do? So if you look at this one, minus 0.2 minus j 0.245 to the power k. This is a complex number. You can write this complex number using what's
Excuse me, sir.
Yeah.
So I think your slides have frozen. We can't see the slide moving.
Oh, really? Because I linked it to another PowerPoint. That's why. So let me share this one. Right. Now you can see it, right?
Yes, sir, we can, sir.
But this is not exactly what I want to share. Let me open the file directly without going through the link. Right. So this is what I was explaining to you, right? Once you break this term expression into 3 partial fractions, you get these 3. Okay. And the partial fractions here are actually complex. Okay. Complex. But process will remain unchanged. And if you look at the first term here, you can see Z over Z minus a constant, and the inverse Laplace Z is this constant raised to the power k. Right? This is what you have seen in
The screen is not shared once again.
can't you see my screen now?
No, so there's nothing shared.
How is it now?
No, now it's visible. Thank you.
Right. Excellent. Sorry about that, Nishad. Right. Okay. So once you break the expression into 3 partial fractions, right? Because you can see the denominator here with 2 complex terms, right? The poles here are actually pair of conjugate poles, right? And when you bring it forward to partial fractions, you will get 2 partial fractions with the complex denominator, right? So like this. And then it's time to inversely transform them to the time domain. Then if you look at the formats here, Z over Z minus a constant. The inverse is the constant raised to the power of k, right? So like over here, 0.5 to the power k. All right. And the second term, again, you can see the Z over Z plus a constant, a complex number here, right? And you have to raise it to the power of k, just like over here. And so is the third term, right? You have minus 0.2 plus j 0.245 raised to the power k. Is that clear? Now, what you do next is that you will see this 0.2 minus j 0.245 in the second term, right? And also minus 0.2 plus j 0.245 to the power k in the third term, right? This is one way of writing the complex numbers, okay? Real part and imaginary part. And there's an exponential format, we call radio coordinate format of writing exponential, the complex numbers, right? Like this. So if you refer to this one, e to the j theta is written as cos theta plus j sine theta, and e to the minus j theta is written as cos theta minus j sine theta. So this is the real part, this is the imaginary part, okay? So what you have here is something like this cosine thing, right? Cos minus j sine and cos plus j sine, something like that. So if you add them together, right, you can get rid of this imaginary part, j sine theta part, and divide by 2, you get cos theta, right? So this way you can convert the complex numbers in the real and imaginary parts into exponential format or into a trigonometric format, sine or cosine, okay? So that's what we are doing over here. We get the, this is as cos theta part, and this is as sine theta part, right? And in front of them, we have 0.826 e to the j 1.234. They are all common, right? But this one is negative, this one is positive. So with that, you get to this for this level here. this second expression can be written as 0.316 to the power k, right? Then e to the minus j 2.225k. And the third term will become like that, okay? What's that in the middle? What's that in the middle? Oops. All right. So let me show it again. Fine. Okay. So we can take 0.826 and 0.316 to the k. This is constant, common to both second and third terms out of the expression, and then you are remaining with e to the j, this one and this one, right? And once you simplify them, you will get it as cosine, right? There's no j here. Is cosine 2.255k minus 1.234, and in front of that you have this amplitude modulated, right, to the power k, and you have a constant to the power k. Okay, right. So it's a bit too long, a bit too complicated, but you need to go through this process if you really want to sharpen your skills, right? And I recommend you substitute k equals 0 to 5, maybe first 5-6 samples, and work it out and plot it, and you can see how the response changes. Okay. Now, once you see that, if you really want to understand what you have done, it's basically this equation, right? There's a system, and there's an input, and there's a response, and the response goes from one sample to the next, and in between we don't know what's happening, right? First sample, second sample, third sample, like that. And now we have a way to calculate these samples. Okay, so we are not dealing with anything but the samples, right? What is the sample now? What is the sample next? What is sample after 2 steps? So we have developed mathematics, which is zTransforms, to calculate these samples. Okay, so there are other things to be explored, whether the system is stable, and first of all, how do we get these equations created from a real system? There are a lot of other things to be explored, but at least you can understand that now, that once you are given this difference equation, right, you can handle it, you can bring it from Z representation to Z world, and then to the time world back again, and then figure out how the sample sequence changes. Okay, right. So that is a pretty good skill to be developed. Before we take a break, is there any questions about what we have covered so far? Right, seems everything is all right. Then let's take a little break, about 10 minutes maximum, right? And I'll see you after the break.